Hello everybody, I'm back with another video. Today we're going to be handling a topic in thermodynamics, which we would usually, I think, call something along the lines of our critical points of any sort of graph. Now, you cover things like critical points in like classical mechanics with things like orbits, right? You have certain points in your orbits graph in which you have a maxima or a minima. And in those moments, the rate of change of your potential is equal to zero, and your maxima will indicate some sort of unstable orbit, and your minima will indicate some sort of stable orbit, right? So you see that a lot in classical mechanics. Similarly, we get critical points also in thermodynamic systems, but instead of obviously something like potential energy with relation to an orbit or something, in free fall, we have something more pertaining to our standard pressure versus volume relationship whenever we hold temperature constant. Now, whenever we talk about critical points in thermodynamics, we're usually referring to the state in which a critical point, in which a value of pressure as it changes with volume is equal to zero, and then also that is true for the second derivative of pressure. So whenever we have our second derivative of pressure equal to zero, and our first derivative of pressure with respect to volume equal to zero, that is what we call our critical point. And we have like one demonstrated here, drawn up in the top left corner. That's graph 8.6.1 in Rife if you have a copy of that book on you. But yeah, so basically we're asked to use the van der Waals equation of state to look for a number of different variables. Namely, we want to look for the constants A and B in the van der Waals equation of state in terms of our critical temperature and our critical volume, which is the associated temperature and volume at the critical point, right? And then we want to find the pressure at the critical point, P sub C, in terms of the critical temperature and the critical volume. And then lastly, using some van der Waals equations of states, we want to basically rewrite the van der Waals equation of state, but instead in terms of parameters T prime and V prime and P prime, right? Now, I'm sorry for the confusing notation here for a lot of the time, but this V character, I'll be careful to say when it is one thing and when it is another thing, because it's a little bit all over the place, right? But V sub C in this particular instance refers to a volume, okay? And I'll reiterate when I'm talking about volume, when I'm talking about volume per mole, and then when I'm talking about moles strictly. So in part A, we have our van der Waals equation of state solved for P, right? We did that in a previous example. If you want to go back and look at that video, I think I'll try and link it somewhere here. If you want to look at that, where we solved for that. So just using information we already have, you plug that into our derivative of pressure with respect to volume. You take said derivative and you set it equal to zero. And then you do the exact same thing with the second derivative. You just plug in your first derivative the first time, or derivate it twice, do whatever you want to do, derivate the way you want to derivate. Just take your derivatives, set them equal to zero, and then what we do is that we want to solve for A simultaneously. So we know that we can get expressions for A in both of those cases because it's the one unknown we have in equation 1 and equation 2. So if we know that those are both equal to A, we can set those equal to each other, and then we can solve for our variable B. And I kind of have it cut off there a little bit at the bottom. But ultimately, once we do the derivatives and set them equal to one another, we should have something like lowercase v cubed, which lowercase v in this case is volume per mole, v divided by nu, divided by 2 times the quantity of R times T, or ideal gas constant R times the absolute temperature T, divided by the quantity of lowercase v minus b quantity squared. And that would be equal to the lowercase v to the power of 4 divided by 6 times 2RT divided by v minus b cubed, or that's lowercase v, not uppercase. On that note, we solve for what b is, and then once we know what b is, we can go to either of our expressions for A, plug it in, and what we should get is that A is equal to 9/8 times the critical volume times the ideal gas constant times the critical temperature T sub C, right? So now that we have that, we can begin to crunch some more numbers. It's really just mostly algebra, and we can use that relationship as expressed in part C down there to try and piece together what some of these constants are equal to in case we need to make some sort of algebraic substitutions. Part B asks us to solve for the critical pressure in terms of C and in terms of V. Once again, it's mostly just algebra, right? We start with our van der Waals equation of state. We plug in our new known variables for A and B, and then we just reorganize in terms of what P ought to be. I think that needs to be P sub C. That's okay. I'm not going to worry about it too much, but I think that is supposed to be P sub C. My notes were wrong, but in part B, that needs to be P sub C. More algebra, more of the same. I've included a couple of the intermediate steps, but once again, it's just plug in A and B, algebraically manipulate some things, and then we just solve for what P ought to be, and when we do that, we get 3/8 times the quantity of R times our critical temperature divided by our critical volume. Now that we have all three of these pieces together, we want to take our original van der Waals equation of state equation and then solve it in terms or at the critical pressure point, right? So we'll start off with what we have for the original van der Waals equation of state as outlined in part B, and then we can make the substitution using the T prime, V prime, and P prime variables and solve them for those terms, right? So we would start off with our van der Waals equation of state with just a P sub C, V sub C, and then T sub C, and then plug in the appropriate ratios, algebraically manipulate them once again, it's just a little bit of tedium to do the algebra. But once we do that, we can get an expression for our ideal gas law, essentially, in terms of with the van der Waals equation of state. We express it in its standard form of pressure being equal to volume. And when we express it in terms of pressure equal to volume, we should have P prime times V prime times the quantity of 3/8 times R multiplied by the ratio of the absolute temperature T divided by T prime over there. So 5.18 in Rife, all you really need to do is know what your equation of state is for van der Waals. You need to know how to take a derivative. You need to know how to do some algebra. That's really all you need in order to do this one, and also have an understanding of what it means to be at a critical point on a graph. Right? When you're at a critical point, your derivatives or your rates of change are equal to 0 for the first and second derivative, at least in this case. And with that knowledge, you can solve for some terms simultaneously if you don't know what they are, and then just recursively plug everything back in and work it over. But yeah, that's essentially 5.18. It's kind of a quick video. It's mostly algebra, so I didn't really think it would be too terrible. Just kind of something neat to explore and to look at and see how we can relate the van der Waals equation of states to actual behaviors of non-ideal gases and how they might relate to other terms like our constants and what what they might look like as they behave on those graphs. That's really it. Nothing much to this one. Let me know what you guys think, and I'll see you guys in the next one.